this is something I use called the Huff model. It's a publicly available model, and it's usually used to determine market share of a potential new store given the location of competing stores. But we can think of parks in the same way. So all of these green areas are protected areas. This is from the USGS Protected Area Database, so it has protected areas on all different levels. And what we have to do in the model is convert them to points, and that's what these yellow dots are. So each polygon is represented by a point. And then the red areas are the census blocks, so that's where people live. And so this data model, depending on your data set, will run overnight, and it'll calculate the probability that any one person will go to any one of these points within the black boundary and within the blue boundary. So if you look at just within the blue boundary on the local scale, there's not that many recreation alternatives. So you get a potential 100% increase in park area, and then you get projected recreation days at that location, and then you have your projected consumer expenditures, given some assumption of how much people spend per day of recreation. But if you put it in this greater data set, you can see as much lower market share, much lower park increase, and a much lower recreation days. Because of course, those people who live in that township can go anywhere in the county, really. But nonetheless, we were able to give them some data as to how many recreation visitors will be there. And I think a good project for this class, and we can maybe get to it later, is how many people who aren't students here visit Evergreen. If this were viewed as a park, which it is for a lot of people, what kind of benefits does that provide the community? So we're not only thinking about recreation as an ecosystem service, but we want to quantify it. How useful is it for people living in Thurston County and Olympia? And then this is a big reason why the wetlands were a huge ecosystem service. So the blue is a FEMA flood area downstream, and this was the area in question. So with the hydrogeography, you can see how the river flows down. And yes, preserving this in wetland isn't going to prevent that whole area from flooding, but you could do a whole analysis of upland, wetland drainage, and deforestation. And of course, the more you're doing that upland, the more you're increasing the liability, the flood liability downstream. And one of the great things, I just want to use this as an example of why an ecosystem service valuation is incredibly useful too, because you can model placeholder values in place of a study that might cost tens of thousands of dollars. If you really wanted to do a flood analysis of this area, you'd have to know the property values of all the places in the blue area. You'd have to know how much water can actually be soaked up by these wetlands. You'd have to do a lot of math, and you need a lot of funding for it. But in the meantime, for relatively low price, you can use ecosystem service valuation. This is a project that Lola and I might be doing, and this is in Eastern Washington. And this is, I've made the background black, and these are the pixels that have changed their land cover designation over the last 10 years. So you can see mostly a lot of yellow and oranges. So a lot has been converted to pasture and hay, grassland, and cultivated crops out there. Not too much reforestation, it's hard to find some green. And then the pink and the red is, of course, sprawl and urbanization. Here's another rendition of that map. So these are your present land covers, and the red are the land cover changes. Here's another project I'm working on for my master's right now. This is an invasive species mapping in King County. So this is the same land cover data set you guys are looking at. That's Seattle up in there. And all those green dots are the data set for this invasive species. So what can we learn from the GIS? Well, I learned, compared to the county land cover, where does this plant prefer to grow in the land cover data set? So you guys could do that for any invasive species here too on campus. Ivy, witch's broom, whatever it is. And then I looked at the land use description as well. And most of the plants are on private property and open space. You can see that parks actually have a low incidence of the invasive species. So people must be doing their job there. And then the habitat, you see stream and riparian areas. Here's another data set from your land cover change, and this was looking at every county and the land cover changes for agriculture and forest, and then this is urban. And of course you can do in relation to the county's own stock of that resource, or you can do gross, right? And because the counties are all different sizes, I wanted to do the top ones. So comparatively, Pierce County is losing the most agricultural land in the state. And the key is standard deviations, the green being positive and the red being negative. So those are outliers from the average. Another project I worked on, I don't know if you guys are familiar with the Deschutes River Estuary Restoration Team, but this was an artist's rendering of what Capitol Lake might look like if it were restored to an estuary. So I volunteered for them, and what we did was we literally had a projector and we asked them, what do you think the land cover would change to? So this is what it looks like presently, and this is what I mapped for mudflats and new wetlands and the old river course. So there we have, again, a before and after. What is the ecosystem service differences for that restoration? Here's another project I did. This is in Tacoma, and they actually have parking occupancy data for every parking area. So the idea was, where is parking redundant? Where do we just have open parking lots that are doing nothing but creating urban decay? Where could we consolidate parks and old parking lots if we tore them up? Where could we expand parks and so on? This was a salmon map we made for copper contamination. This is a better way to look at it. This was the kilometers of road per area for every watershed. This is developed land use per watershed. That is the copper concentration per watershed, and the coho habitat per watershed. So you can see there's definitely a correlation between roads and copper contamination. So when you're thinking about salmon restoration and there's limited funds, you can start to be discerning where are the strongholds, where's the best place to do restoration. Here's a project for Earth Economics, and this was looking at a proposed copper mine in Ecuador and all the communities downstream and all the natural capital it could affect. This is another project we did. This was looking at high-speed rail in California. Do track A or B, which is going to disturb more farmland, which is going to result in more houses having to be moved, more businesses having to be moved. Which one creates the most benefit for the least amount of cost? And you look at the holistic costs and benefits. So again, that's what we're thinking about when we want to look at all the maps, each map. So at this point, I have a lot of other interesting maps to show, we could also do a little bit of a tutorial. I'm inclined to show you some more maps, but are there any questions so far?
More maps.
Any questions?
Bethany's.
What does astounding mean?
I think it means like it blows your mind, basically. Like it grabs your attention. You want to share it with someone. You want to print it out and put it on your wall.
Okay.
The take-home message is clear. I think it's astounding. So this one is global power plant fleet by technology all over the world. I think this one doesn't work so well because the solar seems overrepresented. Anyways, this is cropland data layers for the United States. So you have your different states, and you can see just how systematic and how each region uses its comparative climate and geography to produce certain